According to the National Electrical Code, all electrical systems must be properly grounded and bonded to ensure safety. Bonding the cabinets and racks to the system helps protect personnel and equipment from electrical hazards, such as electrical shocks or damage to equipment. The isolated ground system is intended to protect against ground faults within the transformer primary circuit. However, it does not provide protection for ground faults within the secondary circuit of the transformer or in the cabinets and racks. Bonding the cabinets and racks to the system provides a solid grounding path for ground currents, which helps prevent electrical shocks and equipment damage. Grounding and bonding help suppress electrical noise that can interfere with sensitive electronic equipment. By providing a low impedance path for electrical currents, bonding reduces electromagnetic interference and improves the performance of equipment. Here are recommended steps to take. Firstly, connect the number 6 American wire gauge wire from the copper plate on the wall to the main grounding busbar of the isolated ground system. Secondly, ensure that all panels and equipment within the cabinets and racks are properly grounded using an equipment grounding conductor. Thirdly, test the grounding system to verify its effectiveness. Bonding cabinets and racks to an electrical system is crucial for electrical safety, providing ground fault protection and suppressing electrical noise. When implemented correctly, it creates a safer and more reliable electrical environment. Grounding and bonding are essential practices in electrical systems to ensure safety, prevent equipment damage, and minimize electrical noise. The National Electrical Code provides guidelines on how to properly ground and bond electrical systems. Grounding refers to connecting a conductive object to the earth, providing a path for fault current to flow back to the source. Bonding involves connecting different conductive parts together to create an electrically continuous path. One key reason for grounding and bonding is electrical safety. If a fault occurs in an electrical system, such as a short circuit, the fault current can flow through unintended paths, like a person touching a metal enclosure. Proper grounding and bonding provide a low impedance path for the fault current, causing the overcurrent protection device, such as a circuit breaker, to trip and energize the circuit quickly. This minimizes the risk of electrical shock and injury. Ground fault protection is another critical aspect of grounding and bonding. Ground faults occur when current leaks from an energized conductor to ground. Without proper grounding and bonding, this leakage current can go undetected, potentially causing equipment damage or electrical hazards. Ground fault circuit interrupters are designed to detect even small ground faults and quickly interrupt the circuit, providing enhanced protection. Grounding and bonding also play a significant role in suppressing electrical noise. Electronic equipment is susceptible to electromagnetic interference, which can disrupt its performance. By creating a low impedance path for electrical currents, grounding and bonding reduce electromagnetic interference and improve the reliability of electronic devices. Effective grounding and bonding involve several best practices. The size of the grounding and bonding conductors should be appropriate for the size of the electrical system. The conductors should be installed in a manner that minimizes impedance. All connections should be clean, tight, and corrosion resistant. Regular inspections and tests should be conducted to verify the effectiveness of the grounding and bonding system. The isolated ground system aims to minimize noise. The equipment grounding conductor from each piece of equipment is run back to a single point, typically the grounding busbar in the panel. This prevents circulating currents and minimizes noise. A supplementary ground, using a copper plate and conductors connected to building steel, can provide additional grounding paths and reduce impedance. It's important to bond the supplementary ground to the main grounding system to ensure a common ground potential. The equipment grounding conductor runs with the circuit conductors. It is connected to the grounding busbar in the panel and then to the equipment. This creates a low impedance path for fault current. The size of the equipment grounding conductor should be based on the size of the circuit conductors according to NEC Table 250.122. The National Electrical Code provides comprehensive guidelines on grounding and bonding requirements. NEC Section 250 covers grounding and bonding. It outlines the requirements for grounding electrodes, grounding conductors, bonding conductors, and equipment grounding. The code also specifies the methods for grounding different types of electrical systems and equipment. It is essential to consult the NEC and follow its guidelines when designing and installing grounding and bonding systems. The size of the grounding electrode conductor for a transformer is determined by NEC Table 250.66 based on the size of the transformer's supply conductors. The grounding electrode conductor should be connected to a grounding electrode system such as a metal underground water pipe or a ground rod. The equipment grounding conductor is sized according to NEC Table 250.122 based on the size of the overcurrent protective device protecting the circuit. It should be run with the circuit conductors and connected to the grounding terminals of equipment. When installing a supplementary ground, the copper plate should be securely mounted to the wall and connected to building steel using appropriate connectors. The conductors should be sized according to the NEC and installed in a manner that minimizes impedance. It's crucial to bond the supplementary ground to the main grounding system to ensure common ground potential. Testing the grounding system is essential to verify its effectiveness. Ground impedance testers can be used to measure the impedance of the grounding path. Low impedance is desirable as it provides a better path for fault current. Continuity testers can be used to verify the continuity of grounding and bonding connections. Regular inspections and tests should be conducted to ensure that the grounding system remains effective over time. Effective grounding and bonding are crucial for electrical safety, ground fault protection, and noise suppression. By following the NEC guidelines and implementing best practices, you can create a safer and more reliable electrical system. The goal is to provide a low impedance path for fault current, protect personnel and equipment, and minimize electrical noise. Grounding and bonding are essential components of a well-designed electrical system. Consider the purpose of the isolated ground system. It's designed to reduce electrical noise. It does not provide protection for ground faults. Bonding the cabinets and racks to the system is essential for safety and protection. The copper plate and conductors to building steel can serve as a supplementary ground, providing additional grounding paths. It should be bonded to the main grounding system. Ensure all panels and equipment within the cabinets and racks are properly grounded using an equipment grounding conductor. Test the grounding system to verify its effectiveness. Grounding and bonding are essential for electrical safety, ground fault protection, and noise suppression. The National Electrical Code provides comprehensive guidelines on how to properly ground and bond electrical systems. Effective grounding and bonding involve several best practices. Regular inspections and tests should be conducted to verify the effectiveness of the grounding and bonding system. Electrical noise can interfere with sensitive electronic equipment. By providing a low impedance path for electrical currents, bonding reduces electromagnetic interference and improves the reliability of electronic devices. Grounding and bonding are essential for creating a safer and more reliable electrical environment. When connecting the number 6 American wire gauge wire from the copper plate in the wall to the main grounding busbar of the isolated ground system, make sure the connection is secure and corrosion resistant. Use appropriate connectors for the materials being joined. Ensure that all panels and equipment within the cabinets and racks are properly grounded using an equipment grounding conductor. This includes connecting the equipment grounding conductor to the grounding terminals of each piece of equipment. Test the grounding system to verify its effectiveness. Use a ground impedance tester to measure the impedance of the grounding path. Low impedance is desirable as it provides a better path for fault current. Grounding and bonding are crucial for electrical safety, ground fault protection, and noise suppression. The National Electrical Code provides comprehensive guidelines on how to properly ground and bond electrical systems. Regular inspections and tests should be conducted to verify the effectiveness of the grounding and bonding system. When installing a supplementary ground, the copper plate should be securely mounted to the wall and connected to building steel using appropriate connectors. The conductors should be sized according to the National Electrical Code and installed in a manner that minimizes impedance. The equipment grounding conductor is sized according to NEC Table 250.122 based on the size of the overcurrent protective device protecting the circuit. Proper grounding and bonding are essential for creating a safer and more reliable electrical environment. Grounding and bonding should be part of any electrical system design and installation. It is crucial to follow the National Electrical Code guidelines and implement best practices to ensure electrical safety, ground fault protection, and noise suppression. Electrical grounding and bonding are fundamental concepts in electrical engineering that are often used interchangeably, but they serve distinct purposes in ensuring electrical safety and the proper functioning of electrical systems. Electrical grounding refers to creating an intentional connection between the electrical system and the earth. This connection provides a low impedance path for fault currents to flow back to the source, which helps to protect personnel and equipment from electrical shock and damage. The earth serves as a reference point for the electrical system, helping to stabilize voltage levels and prevent voltage fluctuations. Electrical bonding, on the other hand, involves connecting together all metal parts of an electrical system that are not intended to carry current, such as metal conduits, enclosures, and equipment frames. This creates an electrically conductive path that ensures that all these metal parts are at the same electrical potential. The purpose of bonding is to minimize the risk of electric shock by preventing voltage differences from developing between different metal parts. Grounding and bonding work together to provide a comprehensive electrical safety system. When a fault occurs in an electrical system, such as a short circuit, the fault current flows through the grounding conductor back to the source. If the metal parts of the electrical system are properly bonded together, the fault current will also flow through these bonded metal parts. This creates a low impedance path for the fault current, which helps to quickly trip the overcurrent protection device such as a circuit breaker or fuse, and to energize the circuit. Proper grounding and bonding are essential for protecting personnel from electric shock. When a person comes into contact with an energized metal part that is not properly grounded and bonded, they can receive a dangerous electric shock. However, if the metal part is properly grounded and bonded, the fault current will flow through the grounding and bonding conductors, quickly tripping the overcurrent protection device and preventing the person from receiving a shock. In addition to protecting personnel, grounding and bonding also help to protect equipment from damage. When a fault occurs in an electrical system, the fault current can cause significant damage to electrical equipment, such as transformers, motors, and electronic devices. However, if the electrical system is properly grounded and bonded, the fault current will be quickly cleared, minimizing the damage to equipment. Grounding and bonding also help to reduce electrical noise and interference. Electrical noise can disrupt the operation of sensitive electronic equipment, such as computers and communication devices. By providing a low impedance path for electrical currents, grounding and bonding help to reduce electrical noise and improve the performance of electronic equipment. There are several different types of grounding and bonding systems that can be used in electrical installations. The most common type of grounding system is the grounded system, in which the neutral conductor of the electrical system is intentionally connected to the earth. This provides a low impedance path for fault currents to flow back to the source. Another type of grounding system is the ungrounded system, in which the neutral conductor of the electrical system is not intentionally connected to the earth. This type of system is often used in applications where it is important to minimize the risk of ground faults. There are also several different types of bonding systems that can be used in electrical installations. The most common type of bonding system is the equipment grounding conductor, which is a conductor that is run along with the circuit conductors and connected to the grounding terminals of electrical equipment. This provides a low impedance path for fault currents to flow back to the source. Another type of bonding system is the bonding jumper, which is a conductor that is used to connect together different metal parts of an electrical system. This ensures that all these metal parts are at the same electrical potential. The National Electrical Code provides detailed requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety of personnel and equipment and to minimize the risk of electrical shock, fire, and equipment damage. Some of the key requirements of the National Electrical Code for grounding and bonding include the following. Firstly, all electrical systems must be properly grounded and bonded. Secondly, the grounding and bonding conductors must be of adequate size to carry the fault current. Thirdly, the grounding and bonding connections must be made in a secure and reliable manner. Fourthly, the grounding and bonding system must be inspected and tested on a regular basis. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the National Electrical Code and implementing best practices for grounding and bonding, electrical engineers and electricians can help to protect personnel and equipment from electrical hazards. Ensure to adhere to regulations as outlined in the National Electrical Code.